Okay, so today's lectures are going to be about the multivariate normal distribution. So I imagine you've all come across normal distributions before and probably multivariate normal distributions before. And certainly in one dimension or two dimensions, the multivariate normal is not that hard to visualize. But in higher dimensions, understanding what the, what the structure of a high dimensional multivariate normal looks like takes a little bit of a bit more insight and getting used to. So I want to give you some tools for thinking about what multivariate normals in high dimensions, let's say 10 dimensions or 100 dimensions or even 1,000, 10,000 dimensions, what those kinds of distributions quotes look like. Okay, so that's the big picture goal. So you can do there's two readings here that you can look at. And there's also this interpretation of a multivariate normal from an eigenvalue decomposition, which we're going to go over over now in the video, and I'll make another video about precision matrices. So there are going to be two main points. The first one is related to this eigen decomposition. So it's again, but before we start, just so we're on the same page, as I said, I'm assuming that you've all come across a normal distribution. So of course that has a density that looks something like this. And I expect that you've come across a multivariate normal as well. But if you haven't, in two dimensions, let's see, in two dimensions, if this is x1 and x2, and x1 and x2 have a multivariate normal, let's say with mean 0, and some covariance matrix, the density function in this two-dimensional space has elliptical contours. So if x1 and x2 are independent, you get circular contours, which is kind of a special case. And you can think of this, this is just basically if x1 and x2 are independent univariate normal, then these contours kind of decay in the same way as a univariate normal does. So they're kind of most peaked at 0 and then decay like a bell curve away from 0 in all directions. So that would be the case where they're independent. If x1 and x2 are correlated, then, as I say, you've probably seen these kinds of pictures before. You should have. The contours are elliptical, so this would be a positive correlation here. So I think you can imagine what draws from this density might look like, and you could plot them, and the more correlated they are, you would get the tighter the ellipse looks, and if they were negatively correlated, you would get something that has a goes this way instead. Okay, so in 1 and 2 dimensions, the normal distribution is not that hard to visualize, and I'm if you haven't come across the normal before, just go through that first vignette and simulate some data from a bivariate two-dimensional normal distribution, plot a scatter plot of x1 against x2, and get some intuition for what it looks like. But what I want to kind of focus on is what it looks like if in higher dimensions. So let's suppose that x is multivariate normal in p dimensions, let's say, with some mean vector p and some variance sigma. So the key point I want to get across is that if sigma is symmetric and positive definite, or semi-positive, positive semi-definite, that means none of its eigenvalues are negative. So all the eigenvalues are non-negative. So that is, if sigma is a valid covariance matrix, then it must have what's called an eigen decomposition. So that means we can write, if you like, okay. So hopefully you knew that already. These are the eigenvalues. And these are the eigenvectors. Okay, so these are, so VI transpose VI is equal to 1, and vi transpose vj is equal to 0. They're orthogonal to one another. And okay, so sorry about that. This is a sum here, and this is a sigma. It's a little confusing. So maybe I can just write that out. So that plus lambda. Well, if it's p dimensionals, there could be up to p eigenvalues and eigenvectors, although it could be that sigma is singular, and we'll be focusing. In other words, some of the lambdas might be 0. Okay. And it's conventional for lambda 1 to be the biggest eigenvalue, lambda 2 to be the next biggest, etc., to order them in that way. Okay, so the other thing that you need to know is that if x is, if x is normal p mu sigma in general, then ax is normal a mu a sigma a transpose. Okay, so that's just a general result for the multivariate normal. Okay, so let's now take z to be independent normals 0 0i, let's say. So with the identity now, that one's a nice easy, this is the easiest p-dimensional normal to get your head around, right? Z is a vector of length p, and it's because it's got the identity covariance matrix, that means the elements of Z are independent from one another, right? So even if p is 1,000, you can think about 1,000 independent normals. That's not that hard to get your head around. Okay, so Z's, the easiest very high dimensional normal distribution to get your head around is the one of the identity matrix. So now how are we going to go from there to say something that is more like this? Well, the mean's not hard because you're just adding a mean. So that's really not that hard to get your head around. So let's focus on the covariance matrix. So let's take the matrix that is sum over I. Let's define it to be the sum over I of zi times square root of lambda I times vi. Okay, so let me just, and so v's are a column vector here. Maybe I should have been clear about that earlier as well. These are all column vectors. I didn't. So sorry, the transpose is a row vector. The v is a column vector of height p, and this is a row vector of length p. So that VV transpose is a matrix that's p by p. Okay, so each of these is a p by p matrix. Okay, so here, this is now a vector, a column vector of length of height p. So, and so we're just, these are scalars. Zi is normal 0, 1, of course. I should do it that way. Okay, and lambda, the eigenvalues are scalars, and the v is a vector. So what we're doing here is writing x, which is a column vector of length p, as the sum of several column vectors scaled. So the column vectors in this case are the eigenvectors. Okay. All right. So you can think of forming X as a linear combination of the eigenvectors, weighting each eigenvector by the product of two numbers. One is the eigenvalue, or the square root of the eigenvalue, and the other is a random normal. And if we define X this way, then it's not hard to show that, well, that the so let me just say that zi is normal 0, 1. So the square root of lambda I times zi is just normal 0 lambda I. And if we do vi square root lambda I zi, we know that that's normal 0 lambda I vi transpose. Basically, that's just this, applying this here. Okay, where sigma is a scalar in our case. Okay, so that means by the this is x is the sum of these, so x is normal 0 the sum over I of lambda I vi transpose, because if because it's the sum of these, and these are each normal, and if you sum normals you get a normal. So that's another thing I'm hoping you already know. The sum of two normals is a normal. If you don't already know it, you know it now. And so the sum of a bunch of normals is also normal, and you just add the means and you add the covariance matrices as long as they're independent. And they are independent because the zi's were independent here. Okay, should have added sum of two independent normals is normal with the sum of the means and the sum of the covariance matrices. So okay, so where are we? This of course was sigma. Sorry, sigma, right? This here, this sigma. So what's the point of all this? If I give you a covariance matrix sigma, and I ask you to say randomly draw a multivariate normal with that covariance matrix, you can do that in two steps. First, take the the eigenvalue decomposition, eigenvector decomposition, the eigen decomposition, I guess I should say. The eigen decomposition to get, the lambda i's and the vi's, and then form, the z's, z1 up to zp, 1, 2, and 3. These are independent normal 0, 1. And then set x to be the sum over I of the square root of lambda I times zi times vi. Right. So that's, that's how to generate x normal 0 sigma. So this kind of gives you some insights, especially if sigma here is low rank. Because if it's low rank, that means it's got only a few non-zero eigenvalues. And so this representation is rather simple. So let's do the special case where sigma is rank 1. So, and I'll just give you an example of a sigma that's rank 1. Let's just take the sigma to be the matrix of all ones. Whatever dimension you like. I guess I've drawn it here in 6 dimensions, but you could think of it in 10 or 100 dimensions. So that's a rank 1 matrix. You can see all the columns are the same, all the rows are the same. So it's a rank 1, it's symmetric. And in fact, its eigenvalue decomposition, or its eigen decomposition, is simply, it's 1, 1 transpose, isn't it? And I guess there's a 1 over, there's a scaling factor here that I'm not going to worry about. I can just write it as 1, 1 transpose. So 1 here, sorry, maybe I should say that 1 is, this is a column vector of all ones. Right. So if we did the eigen decomposition, we would get eigenvectors that are like all ones, and essentially we would get that we would just have to do z1 times the column vector of all ones. So this would imply that X is normal 0, 1, 1 transpose. So how can you think about this? Even in 1,000 dimensions, the way to think about this is that X, if it's got this covariance matrix in 1,000 dimensions, is just some multiple of the constant vector of all ones. What's that multiple? It's a random normal. So it's some random normal, standard normal, times that vector that goes in the direction where it's all equal. So X will be, basically X is equal to Z1, comma Z1, comma Z1. You know, all its entries are equal where Z1 is normal 0, 1. Okay, so that's a pretty simple case, but just more generally, if let's say the general rank 1 case where sigma equals V transpose for some V. So X equals Z1 times V would imply that X is normal 0 V transpose, and this is sigma, of course. Okay. So if you've got a rank 1 covariance matrix, you can think of a multivariate normal with that covariance matrix as just having some scalar, some multiple of that the eigenvector V. So the eigenvector tells you which direction the x's will be pointing in, if you like, and the multiple is just a random normal, which basically tells you how far it's going to go from the mean. You know, and so we know that in general, random normals, you know, most 95% of the time they're between minus 1.96 and plus 1.96. So that gives you some idea of what the scale is going to be as well. Okay, so that's a rank 1 case. You know, obviously higher rank gets complicated, but you can kind of now start to think about that the eigenvalues, remember here, they're also going to impact the scaling. So if you've got a sigma that has a few large eigenvectors and most of the rest are, sorry, a few large eigenvalues and the rest are all small, then it's going to, the data that are generated from that normal with that variance covariance matrix are going to kind of lie along these lines, or they're going to be some major multiple, normal 0, 1 multiple of the main eigenvectors scaled by the eigenvalues, and the directions, the eigenvectors that have very little eigenvalues are going to not, there's not going to be much variation in that kind of direction. So that's just an idea to get a way to get your head around low rank covariance matrices and what a multivariate normal might look like if they've got a low rank variance covariance matrix. So in factor analysis, that's an example where people use low rank. So I'm not going to talk about it right now in much detail, but just to mention, factor analysis is an example where the model is that X is a data matrix now. So X is maybe an n by p matrix, L is an n by k matrix, F is a k by p matrix, and E is a n by p matrix. And the assumption, simplest assumption anyway, is that the EIJs are normal, are independent. So in other words, E I or E dot J normal 0, the n dimensional identity matrix. And then the other assumption people usually make in factor models is that the Fs are also IID normal 0, 1. So you can, so if you integrate out F, you get that X given L is actually multivariate normal 0. So you can change the mean if you want. People usually start with the models, which are 0. L transpose plus, maybe I should have said that it should have had a sigma squared here. So factor models is one example where low rank matrices are explicitly used to model covariance matrices. Well, okay, this is a low rank matrix. This is actually, is it actually equal to the sum over K of L K LK transpose, where LK is the kth column of L. And this is N, right? Yes. Oh, and maybe I should have written the way I've written it here. This is a model for X dot J. Yeah. The columns of X have this structure, and sometimes they, you can write the model the other way and have the rows have that structure too. Okay, actually, so this is low rank plus diagonal, right? This is, it's not actually a low rank covariance, it's a low rank plus diagonal, which is the way to think about that is that it's, think about the low rank part. So there's something that's got this low rank low rank covariance matrix, and then you're adding some additional random deviation to every element. So it's, as I said before, in some ways the identity is the easiest one to get your head around. Everything's independent. The low rank is the next easiest to get your head around. And so if you can get your head around both those, you're just adding two random normals, one which looks like one and one which gets the other, to get a low rank plus diagonal. Okay, so the key is this idea that if you're in high dimensions, the directions of the major eigenvectors of sigma, that is the ones with the largest eigenvalues, they're determining the directions that the data will tend to vary most in. That's another way of thinking about it. We'll come back to this idea when we talk about principal components analysis. Okay. Oh, I should say one more thing, which is that you can write this all out in matrix notation as well. I guess I did the matrix notation here for the factor analysis, but you can also do the math in terms of the matrix notation, and actually so in matrix notation you can write D here is the eigenvalues, so you can write it in terms of that's this in matrix notation. So you might, if you prefer to think in matrix notation, maybe that's well, it's there on the dyno list.